So now I'm going to continue with deep neural networks, and I'm going to show you another way of implementing deep neural networks. Import NumPy as NP, import pandas as PD, and you can import all of these Torch packages, including from Torch utils data import tensor dataset data loader, and this represents another way of reading in actual CSV data, and I'm going to touch upon that further on in this lecture. So we can import the data like so. I store my iris data in the variable data underscore set ID. These are the predictors, and this is the response variable species. Since we have things like iris setosa, we have to convert this to a numerical entity. So another way of doing it is by saying species is equal to iris setosa 0 versicolor 1 virginica 2. So this is another way of assigning numerical variables to quantitative factors. And for dataset species item for item in dataset species, so this is actually going to replace iris setosa with 0, versicolor with 1, and so on. And X, now we are going to store these 4 predictors as our X variable, and species are going to be our response variable. We are going to normalize X is equal to normalize X, np.array Y, and we are going to convert it to int as before. Now we are going to split our data into training and testing data set, X underscore train, X underscore test, and so on, and we are going to split X and Y using test size 0.1. So 90% data for training, 10% for testing, and you can see how the split has taken place. Now we are going to use data loader to convert NumPy arrays to tensors, because we have to convert NumPy arrays to tensors before using Pytorch. So again, Torch utils data, it provides a way of loading data into the Pytorch model, and we are going to import data set in data loader, and data loader represents a Python iterable over a data set. So I create 2 variables, train loader, test loader. I call the function data loader, tensor data set. So I'm going to the torch from NumPy is going to be converted. Basically, we obtain a tensor data set. So tensor data set, torch from NumPy as before, X train, Y train. So we do this for the training data set, and then again we use the data loader for the testing data set. So we have the data loaders, train for train loader, validation for the test loader. And indeed, you can try to use this chunk of code for your own CSV data, for reading your own CSV data into Pytorch. Class classifier NN module, and I define my class. And before I go forward, basically I have 3 hidden layers. The first hidden layer with 227 neurons, then with 94 neurons and 75 neurons, and we feed in the 4 predictors, and with the view of obtaining the classification of the 3 outputs. So NN linear for 224 stands for the number of predictors, 227 are the neurons in the first hidden layer, and again the same here, 227 are the neurons in layer 1, 94 are the neurons in hidden layer 2, and 75 neurons in hidden layer 3. And then we obtain 3 classes, so that's why we have 3. So self dropout nn dot dropout, and def forward self x. So now this is where we do forward propagation, and we are going to feed our inputs and the hidden layer weights all into activation functions, the ReLU activation functions. So this is the activation function for 1, FReLU self FC1, and so on. And then we finally obtain the output. Now we are going to use an Adam optimizer to optimize our network. So first I create a variable model, classifier, criterion, NN.N loss, and this is the negative log loss which I spoke about. And here we can even use the optimizer Adam. So if we don't want to use SGD, then we have the Adam optimizer model parameters, and this can be our learning rate, and we can have a greater learning rate or a lower learning rate, and this is what our model looks like. And then we are going to essentially, if we want to calculate how good the model is, I create a function def predict model inputs output model inputs, and this is something we did before. And now we are going to perform forward and backward propagation from torch autograd import variable epochs. So we are going to have 2000 epochs, and we are going to iterate over all of them. So for I features labels in train loader, we are going to have the features and wrap them in the class variable, and labels and wrap them in the class variables. Forward pass, again I set them to 0, features.float, outputs model features, loss, criterion, outputs labels.long, because labels or the response variables, we always convert them to long. We did that before. Loss backward, this is where we do the backward propagation. And the optimizer step. So train loader, ypred, predicted response variables, predict model, torch from numpy x train. So we are going to use the training data for predicting the labels, and the accuracy, we compare the training predictors with the actual training labels with the predicted labels. And then throughout each of the epochs, we start with low accuracies, but eventually our accuracies become much higher. And this is, mind you, the training accuracy. And we can plot our accuracies and loss functions. So anyway, this is the training accuracy, and as you can see, it increased over the number of epochs, and by the time we had 2000 epochs, it crossed 80% accuracy, and this is the training loss. Now we are going to evaluate the test accuracy. So I take my yPredict, the predicted labels, I call the function predict model, torch from numpy. So I implement this model on the testing data set, and I compare the predicted response variable with the actual labels present in the testing data set, and it seems that the accuracy is only 73% in this case. In addition to the overall accuracy, we have other measures of accuracy as well, things like precision, recall, F1 score, and if we want all of these, then we can from sklearn.metrics import classification report, target names, and then we actually print the classification report where we compare the labels present in the testing data set with the predicted labels, like so.